Welcome to today's video on geography, focusing on geomorphology.
Geomorphology is the study of Earth's surface features, like mountains and valleys, and their formation. Rocks are categorized into three main families: igneous, sedimentary, and metamorphic. Quartzite, a common rock type, is classified as a metamorphic rock.
Igneous rocks, or primary rocks, form from the cooling and solidification of molten magma or lava. Intrusive rocks, like granite, cool slowly underground, forming large crystals. Extrusive rocks, like basalt, cool quickly on the surface, resulting in fine-grained textures.
Igneous rocks are crystalline, hard, non-layered, and unfossiliferous. They are solid, shiny, and strong, formed from heat rather than fossils. Examples include granite, basalt, pumice, and obsidian.
Sedimentary rocks, or secondary rocks, are formed from compressed layers of sand, mud, or small particles over time through a process called lithification. They cover 75% of the Earth's surface, but make up only 5% of the crust. Common examples include sandstone, shale, and limestone.
Sedimentary rocks are categorized into mechanically, organically, and chemically formed types. Key characteristics and uses include sandstone for building, limestone for cement, and coal as a fuel source. Metamorphic rocks are transformed rocks, arising when existing igneous or sedimentary rocks change form due to intense heat and pressure without melting. Key processes include foliation, where minerals align in layers, and non-foliated, where rocks lack layers. Common transformations include limestone to marble and shale to slate.
Metamorphic rock formation is a result of heat and pressure acting on igneous or sedimentary rock. This process leads to recrystallization without melting. Examples of foliated, layered rocks are gneiss, while non-foliated, massive rocks include marble. Examples of metamorphic rocks include marble, created from limestone and used for monuments; quartzite, derived from sandstone, known for its hardness; slate, from shale, used for roofing; and gneiss, from granite, recognized by its wavy bands of color.
Regarding global reserves of anthracite coal as of 2017, the United States holds the highest reserves.
Coal is classified by its carbon content and heat energy. In 2016 to 2017, the U.S. ranked first in global coal reserves with 22 to 24% world share, followed by Russia, Australia, China, and India.
The coal progression moves from peat to lignite, bituminous, and finally anthracite. Anthracite has the highest carbon content and heat, and the U.S. holds the largest known reserves. The United States holds more high-grade coal reserves than Russia, China, and India.
Russia is second in overall reserves, but its high-grade coal is lower. China is the world's largest consumer, but has smaller reserves of high-grade coal. India's reserves are mostly subbituminous. India holds the fifth largest coal reserves globally, estimated at over 400 billion tons. Coal is vital, generating over 74% of the nation's electricity, fueling its energy security and industrial growth. Major types of coal in India are Gondwana, about 250 million years old, which accounts for 98% of reserves and production, mainly bituminous. Tertiary coal, 15 to 60 million years old, has high moisture and sulfur, and is found in northeastern states, including lignite in Tamil Nadu.
Now, the next concept explains the types of coal in India. The image shows that most coal is Gondwana coal, found in peninsular regions like the Damodar Valley, while tertiary coal is found in northeastern states, such as Assam and Meghalaya. It also highlights lignite, brown coal, mainly present in Neyveli, Tamil Nadu.
Over 90% of India's coal is concentrated in just 5 states. Jharkhand is number 1 with about 26.4%, and Odisha is close behind with about 25.1%. Chhattisgarh, West Bengal, and Madhya Pradesh also contribute significantly to the total reserves. Let's review a geography quiz question from 2018. Which statement about glacial topography is incorrect? The correct answer is D, that depositional activity makes hanging valleys. Hanging valleys are actually formed by glacial erosion, not deposition.
Glacial topography is the land shape created by glaciers, which cover about 10% of Earth's land. Glaciers are crucial for freshwater storage and serve as climate archives. However, melting glaciers pose an environmental risk of glacial lake outburst floods, or GLOFs.
Now, the next concept explains erosional landforms formed by glaciers. The image shows two main processes: plucking, where glaciers pull and break rocks, creating rough surfaces, and abrasion, where moving ice smoothens the land like sandpaper. These processes form features such as cirques, arêtes, horns, U-shaped valleys, hanging valleys, and fjords, shaping rugged and polished landscapes.
Now, the next concept explains glacial depositional landforms. The image shows how glaciers deposit rocks, sand, and soil to form features like moraines, lateral, medial, and terminal, which are ridges of debris. It also highlights drumlins, eskers, outwash plains, and kettle lakes formed by melting ice and flowing water. These landforms indicate how glaciers shape and modify the landscape through deposition.
Now, the next concept explains erosional landforms formed by glaciers. The image shows two main processes: plucking, where glaciers pull and break rocks, creating rough surfaces, and abrasion, where moving ice smoothens the land like sandpaper. These processes form features such as cirques, arêtes, horns, U-shaped valleys, hanging valleys, and fjords, shaping rugged and polished landscapes.
Now, the next concept explains glacial erosional landforms in a visual way. The image shows how glacier movement shapes the landscape into features like cirques, bowl-shaped hollows, U-shaped valleys, arêtes and horns, sharp ridges and peaks, hanging valleys with waterfalls, and fjords, sea-filled valleys. These landforms are formed mainly due to processes like plucking and abrasion, which carve and reshape the terrain.
Returning to the quiz, option A states that glacial topography is parasitic, which is correct because glaciers modify existing landforms. They transform pre-existing V-shaped river valleys into U-shaped valleys.
Another quiz question from 2018 asks what the process that shapes the Earth's surface is called. The correct answer is D, geomorphic process.
A geomorphic process is the natural action that alters the Earth's surface. These forces are classified as endogenic, forces from within that build the land, and exogenic, forces on the surface that wear down the land.
Options A, B, and C for the previous quiz question are incorrect. Geosophical is not a scientific term. Hypographic relates to elevation, not a surface-shaping process. Tetrahydro is a chemistry term. The word breakdown shows that morph means form or shape, and graphic means to measure or describe, emphasizing how etymology aids in understanding scientific terms. The last quiz question from 2018. A U-shaped valley is formed by... The correct answer is A, glaciers. The other options are agents of coastal erosion or V-shaped valley formation.
Now, the next concept explains the formation of a U-shaped valley by glaciers. The image shows that originally a V-shaped valley is formed by river erosion, which is narrow and deep. When a glacier moves through this valley, it erodes both the valley floor and sidewalls through processes like plucking and abrasion, making it wider and flatter. As a result, the valley transforms into a U-shaped valley, which is broad, flat-bottomed, and steep-sided.
Comparing the two valley types, V-shaped valleys are formed by vertical river erosion and are narrow at the bottom. U-shaped valleys are formed by glaciers, featuring wide, flat floors and steep vertical walls, a result of deepening and widening erosion.
Let's move on to question 6. The Black Forest Mountain is an example of what type of mountain? The correct answer is B, block mountain. The Black Forest is a block mountain, not a horsed mountain, which is a more specific term for the uplifted part. It is not a volcanic or folded mountain, as it formed through tectonic faulting rather than lava or compression. Fold mountains are formed when tectonic plates collide, causing the crust to crumple and fold. This process is driven by compression, resulting in upward folds called anticlines and downward folds called synclines.
Examples of young fold mountains include the Himalayas, the Alps, and the Rockies. these massive ranges are still actively forming due to ongoing tectonic plate collision.
This picture shows the formation of fold mountains caused by the collision of tectonic plates. When plates move towards each other, intense compression forces bend and fold the rock layers, creating upward folds called anticlines and downward folds called synclines, resulting in the development of fold mountain ranges.
Young fold mountains formed during the Tertiary period, about 10 to 25 million years ago. They are characterized by great heights, sharp peaks, and rugged slopes, and they continue to rise due to active tectonic pressure.
Old fold mountains formed over 66 million years ago during earlier orogenic events. Because of their age, they have been subjected to significant erosion, resulting in lower elevations and rounded features.
Block mountains are formed when faults appear in the Earth's crust, causing vertical displacement. The raised blocks are called horsts and form the mountains, while the lowered blocks are called grabens and form the valleys. Examples of block mountains include the Black Forest in Germany, the Sierra Nevada in the USA, the Vosges in France, and the Vindhya in India.
This image visually represents the formation of block mountains, illustrating the horsts and grabens created by faulting in the Earth's crust.
Old block mountains, like the Vosges and the Black Forest, feature lower elevations and gentler features due to prolonged erosion. Their formation is driven by internal tension forces that break the crust. Volcanic mountains are created when magma erupts and piles up on the surface, forming cone-shaped mountains. They are built layer by layer from lava, ash, and rocks.
This picture shows the formation of volcanic mountains, where magma from beneath the Earth rises through a magma chamber and erupts as lava, ash, and gases. Over time, repeated eruptions deposit layers of lava and ash around the vent, building up a cone-shaped volcanic mountain with a crater at the top. This picture shows the global distribution of major volcanoes across the world, highlighting both active and extinct ones. It clearly indicates that most volcanoes are concentrated along tectonic plate boundaries, especially around the Pacific Ring of Fire, as well as in regions like the Mid-Atlantic Ridge and parts of the Mediterranean and East Africa.
Now, the next question focuses on the origin of the Himalayan ranges, specifically the formation period of the Middle Lesser Himalayas. This question checks your understanding of geological timelines and the multi-stage development of the Himalayas. The Himalayas were not formed in a single phase, but evolved over millions of years during the Cenozoic era due to continuous tectonic uplift. Among these stages, the Middle Himalayas originated during the Miocene epoch, making option B the correct answer.
Now, the next concept explains that the Himalayan ranges formed in different stages over time due to the collision of the Indian and Eurasian plates. The Greater Himalayas were formed during the Eocene epoch, the Lesser Himalayas during the Miocene epoch, and the Shawalic ranges during the Pliocene epoch. This shows that the Himalayas developed gradually and are still rising today due to ongoing tectonic activity.
Now, the next concept explains the tectonic forces behind the formation of the Himalayas. The image shows that the Indian plate is continuously colliding with the Eurasian plate, convergence, leading to strong compression. This causes deformation of the Earth's crust, resulting in the uplift of the Himalayas and the Tibetan Plateau. It also highlights the role of microplates, such as the Burmese microplate, making the region tectonically complex and active even today.
The Western Ghats are not true block mountains. They are classified as a great escarpment or residual mountain range. They were formed by the faulting of the Indian plate during continental rifting, but lack the classic uplift between two faults.
This image illustrates the journey of continents over 225 million years of drift, from the supercontinent Pangaea to the modern configuration of Earth today.
The correct mismatch is bahada, winds. A bahada is a landscape feature formed by the merging of alluvial fans, a fluvial or water-driven process in arid environments, not an aeolian or wind-driven one.
This summary categorizes landforms based on their geomorphic agent, such as running water, groundwater, glaciers, winds, and sea waves, distinguishing between erosional, wearing away, and depositional, building up features.
Distribution of fossils in different continents is not taken into account for seafloor spreading, which relies on volcanic activity, magnetic stripes, and the age of rocks. Fossil distribution was key evidence for continental drift. Seafloor spreading begins with cracks at the bottom of the ocean, called mid-ocean ridges. Molten magma rises, cools into new rock, and pushes the older seafloor away from the ridge, causing the ocean basin to expand. 3 key facts support seafloor spreading: volcanic activity at mid-ocean ridges, magnetic stripes in ocean floor rocks, and the age of rocks being youngest at the ridge and older moving outward.
Biogeographic evidence, such as the fossil remains of Sinognathus, Lystrosaurus, Mesosaurus, and Glossopteris across different continents, supports the theory of continental drift.
Evidence for continental drift includes the jigsaw fit of continents, the distribution of identical fossils, matching mountain ranges and rock types, and climate clues from ancient glacial deposits found in presently warm areas.
Thank you for your time and attention to this video.